Hello everyone, my name is Aristarchus and I'll be handling seminar 2. If you have any questions regarding this seminar or any other relevant course material, you can always shoot me an email. The topics which I'll be covering in this seminar will be linearization. Like if you are given a nonlinear ordinary differential equation, like how to linearize it and why do we linearize it. And then we'll see a simple modeling exercise. Then the third example will be a Laplace transformation problem. So let me read out the question first and then I'll try solving the problem. So question 1. Linearize the following equation around the steady state point y bar comma u bar and put it in deviation variable form. So the given equation is dy by dt is equal to minus 5y square plus 3uy plus 6u square. From the question, so we know that the steady state point is y bar comma u bar and the model equation is given here. So why is this nonlinear in the first place? So we have y square, which is a square term, and then we have in the second term, like 3u and y, we have a product of two terms, and then in the third part we have u squared, so which is nonlinear as well. So this is a nonlinear function, and so we have been asked to linearize this nonlinear ODE. And what is the motivation for linearization? So in process control, many times you'll be deriving mass balance equations and you'll mostly land at nonlinear differential equations. And then to find the solution of these nonlinear differential equations, you have to integrate them. And when the model is getting highly nonlinear, it is always not possible to integrate them analytically, or it might be very difficult. One trick which you would be learning in this course is to convert the ordinary differential equations into algebraic equations and then solving them. So this will bypass the numerical integration process, like you don't have to integrate them explicitly. So for implementing Laplace transform, your differential equations have to be linear. So that is why we are interested in linearizing the model in the first place. So using Taylor series expansion around the steady state point, nonlinear model can be converted to a linear model with the formula given below. And we know that at steady state there is no dynamics, which means the states don't change. So the differential d by dt of the state would be 0 at the steady state point. So the formula simplifies down to the one given here. I've given the formula and the model equation on the upper right corner. So the only difference from the general formula would be here the variables are y and u. So now let's find out all the terms which are in the formula so that we can plug them into the formula and then get our solution. So we know that the first term on the right hand side of the formula is f of x bar comma u bar, which is like the function value at steady state. That will be 0 because the system has no dynamics at the steady state point. So now let's go to the second term, which is dou f by dou y. So if we evaluate dou f by dou y here, we would get minus 10y from differentiating minus 5y square, and then plus 3u when we are differentiating the second term of the model, and 0 when we are differentiating the third term of the model, because 6u squared is a constant. So if we are going to evaluate that at the steady state point y bar comma u bar, we get minus 10 y bar plus 3 u bar. So the same goes for the second term, dou f by dou u. So dou f by dou u will be equal to 3y plus 12u. In this case, the first term minus 5y squared will be constant, so it goes away in the when you're differentiating. And then we evaluate that at the steady state point y bar comma u bar. So dou f by dou u becomes 3y bar plus 12u bar. So now we plug all these information into the general formula. So we get dy by dt is equal to dy bar by dt plus dou f by dou y into y minus y bar plus dou f by dou u into u minus u bar. So I'm taking this dy bar by dt to the left hand side. And if I pull the differential operator out as common on the left hand side, I get d by dt of y minus y bar, and then the entire equation on the right hand side. So we have been asked to write the linearized model in terms of deviation variables. So I introduce deviation variables. Y dash is equal to y minus y bar, and u dash is equal to u minus u bar. So in that case, the final solution will be d of y bar by dt, and here in the place of y minus y bar and u minus u bar, I substitute y bar and u bar. So this is the solution for the first question. So when we are asked to find the linear model from a nonlinear ODE, so first you have to write down the formula, the general formula which is on top, and compute each of the terms in the formula, plug it in, and then finally write it down in terms of deviation variables. So now let's go to question 2. In question 2, you have been given a CSTR with 2 inputs and 1 output, and the tasks which we have to perform are to derive a dynamic model for the mass fraction XA, and then degrees of freedom analysis on the model equations, and then finally linearization. So in this question, we'll be seeing how to derive the mass balance equations, degrees of freedom, and then linearization. So this is like a complete repetition of what we have done in question 1 with some modeling involved. So here, let me read out the important points which they have given to you in the question. So the components FA and FB are both pure, which is mentioned right here. FA, which is pure component A, and FB, which has no A. So both of them, FA has only A and FB has only B, and they are mixed in the reactor. The flow FA is constant. It should be noted that the flow is constant here. The system is initially at steady state. Starting from time t is equal to 0, the flow rate FB is varying. And then the assumptions have been laid down. It's always good to summarize the information which has been given in the question so that you don't miss out important points. So the information given in the question is like both the input streams are pure. No mixing has happened before entering the CSTR. CSTR is a continuous stir tank reactor. FA and FB are the volumetric flow rates. The flow FA is constant. And the assumptions in this model. the densities of both the streams are same and constant. So that if density of the stream A is rho A and the density of stream B is rho B, they are both constant. So we can write rho A equal to rho B is equal to rho. And then the tank is well mixed so that there is no density change on mixing. The volume of the tank is constant. So now let us see how to derive the mass balance equations for the component A in the exit stream. General mass balance equation would be accumulation in the system is equal to input minus output plus generation. But here there is no generation, so we can safely assume generation is 0. But there are 2 inputs and 1 output. So the mass accumulation would be equal to density into volume of the system. We know that the volume of the system is V. So d by dt of density into volume is equal to the mass coming in through the first stream would be equal to the density into the volumetric flow rate of that stream. So density into Fa plus the second stream's mass flow rate would be density into Fb minus, in our assumption we have been given that there is no change in density by mixing, so the density in the output stream would also be rho. So the output is rho into F out, if F out is the output volumetric flow rate. So this is the equation if you will arrive at, if you start deriving. And then because density and volume are both constant in this problem, so d by dt of rho into V, rho and V both are constant, so d by dt would become 0. So in that case, if you simplify the mass balance equation, what you would get is Fa plus Fb is equal to F out. Let this be equation 1. And if we write down the component balance for A, we get, so the information given in the system was stream B does not contain A because B is pure, it contains only B. So the component balance for the system with respect to A would be d by dt of rho into V into Xa, which is the mass fraction of A accumulation. And on the right hand side, the input rho into Fa into 1 because the stream Fa contains only A, it is 100% pure. So we have a factor 1 here. And then Xa is the mass fraction of A in the outlet stream, so the output would be rho into F out into Xa. And then we know that density is constant, so we can pull it out of the differential term, and then if we cancel it, and also V is constant, so we can pull that out as well. So we get V into dxa by dt, which is equal to Fa minus F out Xa. So let this be equation 2. Both equations 1 and 2 describe the dynamics of this particular model. So now if we had to do degrees of freedom analysis, so we take the model equations and then we see if we have any parameters in the equations and the number of variables which are remaining, and then we will see if the system can be solved for a unique solution or not. So we have 2 equations here like we saw in the previous slide. So the number of equations would be 2. And then we know that the volume inside the tank and the flow rate FA is held constant. So both these will become the parameters for the model equations. And if you count the number of remaining variables, we have 3 remaining variables, which are FB, Fout, and XA. Degrees of freedom is equal to the number of variables minus the number of equations. So in this case, it would be 3 minus 2, which is 1. So we have 3 variables and 2 equations. So we'll have infinitely many solutions if we are trying to solve. So we have to fix one variable as the input to get a unique solution for the system. So here Fout and XA are both output variables, so it makes no sense to fix them as input variables. So the only option for us is to treat FB as the input variable. In that case, if you fix FB as the input variable, then there will be only 2 variables which are remaining, and we have 2 equations, so we'll get a unique solution if you're trying to solve. So this completes a degrees of freedom analysis. So in the third subdivision, you have been asked to linearize the derived nonlinear model. So if you substitute equation 1 into equation 2, what you get is equation 3, which is written right here. So why is this equation nonlinear? Because we have a nonlinear term, FB, which is an input, XA, which is a state variable. So we have the product of input into state variable. So this is a nonlinear term. And the first term on the right hand side, FA, is constant. We know that the flow FA is held constant. And the second term, state into a constant term. So that will also be a linear term. So the nonlinearity in the model is coming because of this third part. So we follow the same procedure which we followed in question 1. I'm going to put the same formula here. And then if you compute the partial derivatives with respect to x and u and then plug it into the equation, you should be getting the linearized differential equation. So the equation which we are going to linearize is given on the top. And then if we use Taylor series expansion around the steady state point x bar comma u bar, here x is XA, which is the state variable, and the input u is FB. So wherever there is an x in the formula, we put XA there, and wherever there is an u, we put FB there. And we know that at the steady state point there is no dynamics, so the function value at x bar comma u bar is 0. So the simplified linearized model will be the one which is given at the bottom. So let's compute the terms which are required for substituting into the general formula. So if we see here, we need dou f by dou capital FB, and then we need dou f by dou XA computed at the steady state point. So let's compute dou f by dou FB first. So when computing dou f by dou FB, both the first and the second terms on the right hand side of F becomes 0. And if you differentiate minus FB of XA, we get XA, because when you differentiate FB, it becomes 1. And if you evaluate it at the steady state point, we get dou f by dou capital FB is equal to minus XA bar. Similarly, for the second term, like dou f by dou XA, what we would get is minus FA into minus FA minus FB. And evaluating that around the steady state point XA bar comma FB bar, we get dou f by dou XA is equal to minus FA minus FB bar. So if we plug all these into this equation right here, we should be getting the linearized model. So I'm substituting everything into the main equation, and what I would get is right here on top. And then generally we would write the linearized model in terms of deviation variables, because when you implement a controller, so it is more easier to work if your model is in deviation form. So here we declare the deviation variables. Xa bar, xa dash is equal to xa minus xa bar, and fb dash is equal to fb minus fb bar. So we substitute wherever there is xa minus x bar with the xa dash and fb minus f bar with fb dash, we would get the equation, which is right here. And then if you rearrange, bring the volume to the denominator of right hand side, we would get the equation in this form. And this is the solution for question 2. So now let's look at our final question. So in our final question, we have been given a function f of t in graphical form, and then we have been asked to compute the Laplace transform for this function. So to solve this, we first have to know how to convert this graphical data into an equation, and then we use the Laplace table formula to get the Laplace transform of this function, which is f of t. So from the information given in the question, if I observe it very closely, I can see that there are 3 step changes. The first step of magnitude 5 is at time t is equal to 0. So I can tell that the first step of magnitude 5 occurs with time delay 0. And then the step of magnitude minus 4. Minus 4 is because 5 is the initial magnitude and then it drops to 1. So it is a negative step from 5 to 1. So we can take that as a negative step of magnitude 4 with delay 2. And then it is being held constant. And then finally, there is a third step of magnitude 1 in the negative direction again at t is equal to 6. So we can say a step of magnitude minus 1 occurs with delay 6. So this function f of t is actually 3 step functions. So we'll see how to write this down as an equation. If s t is the unit step change, then the original function f t can be written as the sum of the 3 step functions which we saw in the last slide. So f of t will be equal to the first step plus the second step plus the third step. But we have to be very careful with the delays of each of the steps. So let us write down the first step. 5 is the magnitude into unit step. So it is 5 into st. And there is no delay. So it will be just st. And then if the second step would be minus 4 because it is a negative step from 5 to 1. So minus 4 into s of t minus 2. So there is it occurs at t is equal to 2. So there is a delay of 2 seconds or minutes or whatever time unit. And then the final step is of magnitude 1 in the negative direction, because it drops from 1 to 0. So the final term would be minus s of t minus 6, because it occurs at time t is equal to 6. So the delay is 6 seconds or minutes. So the original function f of t will be sum of these 3 step functions here. Laplace transform is a technique to convert a differential equation into an algebraic equation. So you'll be solving a lot of problems. Laplace transform. But here we are just asked to compute the Laplace transform of this function, which is given here on the top. So on the right, if you see, I have put the Laplace formulas for a unit step and a unit step with a delay theta. So Laplace, L stands for Laplace operator. So Laplace of the unit step s of t is equal to 1 by s. And the Laplace of s into t minus theta is equal to 1 by s into e power minus s into theta. So we'll be using both these formula here. So let's go to the first step. Laplace of the function f of t is equal to Laplace of the entire equation, which is on the right hand side. So the Laplace operator can be split over addition or subtraction. So the Laplace of this equation would be equal to the sum of the Laplaces of the individual terms. So I am taking the Laplace to each of the terms here. And then the Laplace of a constant number is a constant again. So I can pull the constants out of the Laplace operator. So what I would get is given at the bottom. And so now we'll apply Laplace transform with the formula given on the box on the right hand side. So the Laplace of a unit step s of t would be 1 by s. So for the first term on the right hand side, it would be 5 into 1 by s. And for the second term, we have theta is equal to 2. So if you follow the formula here, so it would be minus 4 into 1 by s into e power minus 2s. Similarly, for the third term, it would be minus 1 by s into e power minus 6s. And then finally, I'm just pulling out 1 by s because it is common across the terms. So I would get 1 by s into 5 minus 4 into e power minus 2s minus e power minus 6s as the final solution. So you can check there's a table for Laplace transform. So it has information for the Laplace transform of a step or step with delay or ramp. You can just type it on Google and it'll give you the Laplace formula table, which you can use for solving problems if you have been asked to use Laplace transforms. So this completes our seminar 2. So if you have any questions related to these questions, please reach out to me. Thank you, and I'll meet you guys again in seminar 4.